Waals equation. Ideal versus non-ideal behaviors of gases. The ideal gas, the properties are volume of gas is negligible, means we can ignore the volume of gas when we compare to the volume of container. And intermolecular forces between gas particles are also negligible, means you can ignore the intermolecular forces between gas particle in the ideal gas. For real gas behavior, the gas particles have a certain volume and occupy some space. It's different from ideal. For ideal, you can ignore the volume, but for real gas, you have to consider that it has certain volume and occupy some space. And next, there is intermolecular forces between gas particles for real gas. For ideal gas, you can ignore the intermolecular forces, so we assume that there is no intermolecular forces for ideal gas, but for real gas, there is intermolecular forces between gas particles. These are the difference between the behaviors of ideal gas and real gas. The deviation of gas from ideal behavior due to two factors, volume and intermolecular forces. So gas particles occupy space, so means they have volume. This is the deviation from ideal behavior. And next, the existence of intermolecular forces between gas particles means we consider that there is intermolecular forces between the particles. Condition for deviation of gas from ideal behavior, so means from ideal to real gas. These are the condition: high pressure factor and low temperature factor. For high pressure, volume of container decreases. When you put high pressure, the volume of the container decreases. So the gas particles in the container are closer to each other, occupy a space portion in the container. The volume of gas particles is significant, means now we consider the volume of gas particles. And the intermolecular forces between molecules become significant as well. That is for high pressure factor. When the pressure is high, when you put high pressure, volume decrease, gas particle closer to each other, volume of gas is significant, intermolecular forces between molecules become significant. When the temperature is low, another condition for the gas to deviate from ideal behavior, when the temperature is low, the kinetic energy of the gas particles decreases because it doesn't have energy for gas to move around because the temperature is low. Temperature is low, kinetic energy of the gas particles decrease. Gas particles move at low speed because low kinetic energy due to low temperature. So that's why it moves at low speed. When it moves at low speed, we know that when the gas particle close to each other, there will be intermolecular forces. Because when the gas particle move at low speed, they will be close to each other, so the intermolecular forces between molecules become significant. These two are the factors or the conditions for the gas to deviate from ideal behavior, means it wants to be the real gas behavior. Waals equation, we're going to look at the equation when the ideal gas equation deviate to the real gas equation. So means initially we've learned about the gas is ideal gas. So ideal gas, we know that we don't consider the intermolecular forces, we don't consider the volume of the gas, but when this is the van der Waals equation for ideal gas, PV equal nRT. For ideal gas, when the intermolecular forces is not considered, the volume is not considered. But when it is not ideal gas, when it is real gas, it's real gas, so the properties are different. We already take account the intermolecular forces, we take account the volume, so you cannot use this equation anymore for real gas. This is for ideal gas equation. For real gas, it will become like this: P plus n square A over V square times V minus MB equal nRT. So for real gas, you have to adjust the pressure up and you have to adjust the volume down. This is van der Waals equation for real gas. This one for ideal gas, this one for real gas, where A and B are van der Waals constant. So different gas will have different constant. Different type of gas have different constant. A, this one, relates to the number of electron, relates to the complexity of a molecule and the strength of its molecular attraction. So means its intermolecular forces. Here we already consider intermolecular forces in real gas, and B relates to molecular volume, so we have to consider the volume of the gas. In ideal gas, we don't consider the volume and intermolecular forces, but in real gas, we consider the volume of gas, we consider the intermolecular forces or molecular attractions. So that's why we have to adjust PV equal nRT to become P plus n square A over V square times V minus MB equal nRT. This is the van der Waals equation for real gas. So when you adjust P up, what happened? So this is initially the pressure external too far apart to interact. So this is for ideal gas, we don't consider the intermolecular forces, but in real gas, when the molecules are close to each other, when you put the pressure, we want to deviate the ideal to real, deviate the ideal properties to real gas properties. So we put the pressure, remember deviation, high pressure, so you put pressure. When the pressure is high, the ideal will deviate to become real gas. So when it becomes real gas, we have to consider the molecule's position. When the molecule close to each other, it will have intermolecular forces. So that's why you have to adjust the pressure up for real gas equation. Increase the pressure, adjust pressure up. And volume down. So volume, the volume that we consider here in ideal gas, we don't consider the volume of the gas. We take it as it is. If the container volume is 15 liter, for example, if the container volume is 15 liter, so the gas can move around in 15 liter of container. But actually, in real gas, it cannot really move around 15 liter of container, because you have to take account the molecule or the gas particle take the space of the container. So it might not be 15 liter. When the particles fill the space in the container, the particle itself probably fill some space. So volume available for molecules to move is less than the volume of container, because some spaces are occupied by the molecules itself. So that's why you have to adjust the volume down to mean this volume of container that the gas can move around, because some spaces already taken by the molecule space. Next, condition for real gas to become ideal gas behavior. So this is different from before. Before, from ideal to real. Now, real to approach ideal. It's the other way around. When you want to approach ideal, so it has to be different from before. It has to be the opposite from before. From ideal to real, you have to put high pressure. Now, from real to approach ideal behavior, you have to put low pressure. Why do we have to put low pressure? Because we don't want the intermolecular forces attraction. Because in ideal gas, we don't consider intermolecular forces of attraction. If you don't want to consider the intermolecular forces, you must make sure the particles are far apart. If the particles are far apart, then the gas particles will not interact with each other. So when they are not interact with each other, it won't have intermolecular forces. So that's why if you want the real gas to approach ideal behavior, you have to put low pressure. Low pressure means volume of container increases. When you have big space for the gas particles are far apart from each other in a large volume. So when it's far apart from each other, the intermolecular forces between particles are negligible, means you can ignore the intermolecular forces because they are far apart from each other. Because volume of gas is too small compared to the container, thus it obeys kinetic molecular theory. Ideal gas obeys kinetic molecular theory. Next factor, high temperature. When the gas has high temperature, the kinetic energy of gas particle increases. The gas particles move at high speed because it has high kinetic energy, so it moves at high speed and free from intermolecular forces. The intermolecular forces between particles are negligible, thus it obeys the kinetic molecular theory.